Hello, everyone. Thank you for coming and to visit our presentation. We are Team 8. This is the Transverse System for Fluid Structure Observation. I'm Levi, the team lead. Nate Bender is our technical lead. Noah Leitner is our controls lead. And Tallman Clayton is our communications and purchasing lead. And our advisor is Dr. George Chury. A little background. Our project is to build a cart that mounts atop a rail, and it can hold either two cameras or a camera and a laser pointer, and will follow the flow of fluid through a tube, and it will match the speed of the fluid, and it will capture what George calls fluid structures.
So the design phase we've broken up into several parts. The first phase being the preliminary design phase. So this is where our group was meeting to brainstorm ideas and go over our requirements that we were given by George Chury, Dr. George Chury. Such requirements as we need to accommodate various sensors and cameras, maintain a velocity of 1 meter per second for roughly 1.2 meters, handle a payload of around 65 pounds, be able to adjust two sensors independently of each other, as well as having both coarse and fine adjustment for those sensors. One sensor would be level with the ground, pointing at the side of whatever you're looking at, and one sensor could be pointing down perpendicular to that other sensor. These other categories that we were looking at to help guide our brainstorming sessions were sensor adjustment, power, frame design, and deceleration. The next thing was narrowing down our brainstorming session ideas, and this is what we've come up with, was using the provided rails and motors, a Domino electric linear rail, and an Allen Bradley motor, which we had provided from Dr. George Chury. As well as our design would be made from extruded aluminum, seen in the bottom left. We had a lot of 3030 aluminum that we obtained. And then using a Husky table from Home Depot as a mounting structure. This has several benefits. One being we can mount stuff directly to the wooden surface by screwing stuff in, as well as it is height adjustable. So this would take care of a lot of our coarse vertical adjustment. So the first thing that we did when we acquired these motors and had some of our specifications was do some simple calculations to determine if our motors would be able to handle what we needed. So this is some rough calculations to determine the required horsepower of the motor. So the Allen Bradley motor that we had a maximum of 2 horsepower output. So we did some calculations with the cart weight, the available traverse length, and how far we actually wanted it to travel, as well as the desired velocity and the initial velocity to give us our power in watts, which we then converted into horsepower. The next step was gathering CAD models. As you can see in the bottom left, some of our CAD models were very complicated, such as for the rail, and we needed to be precise with some of our mounting dimensions or else it would not fit together properly. So we gathered them from various sources, such as GrabCAD, and we also modeled a lot of our own, as seen on the right, which is the motor and transmission assembly. So next was the actual design. So we opted for a modular cart design using was the first version in the bottom left. So we could just make 2 identical carts and then mount them, as you can see on the right, one at the bottom and one perpendicular at the top. This design was very good for us because it was machined out of provided materials that we had, so we didn't have to purchase many materials. And then we also were able to make an adapting plate for the bottom of the cart, seen in the right, to the rail cart that was already affixed to the rail for driving it. The next process was designing rail supports to support the weight of the rail as long as everything that was mounted to the cart, which was sat on the rail. So these supports had to be able to hold both the vertical weight the vertical load and the terms of weight of the rail, as well as a horizontal acceleration on the like shear force on the bolts. So we would have two of these supporting the rail. So then after all this was done, we did some hand calculations to determine that the cart that was mounted to the rail was actually able to support what loads we were wanting to throw at it. So in the middle of this page, you can see the torque axis diagram. This was provided in the documentation with the rail, so we are able to know what kind of load maximum loads we would see. And then on the right side of the screen, you can see of all of our calculations, with each column being different situations. So the first is a cart with no sensors, then a cart at the maximum like awkward position. As you can see, it's raised all the way up, pushed all the way back, and then the cart with sensors, and then the cart with sensors at that maximum configuration. So then this allowed us to adjust where we wanted the cart mounted to give us an optimal center of gravity, as well as increase our factor of safety on the cart. So if we look at the bottom, we can see our lowest factor of safeties in the X direction being along the rail, uh, and then we can see our lowest factor of safety is 17. That factor of safety is included with the dynamic load. So at acceleration, that would be our lowest factor of safety. So the next step was doing the FEA simulation on our designed parts. So all simulations assumed a 65-pound load on the cart, as well as a maximum acceleration of 5 meters per second. In our initial calculations, we determined that the necessary acceleration would be around 4.7 meters per second, so we rounded this up to 5. And this was ran on all critical components with a target of 10 or more as a factor of safety for all of the components. Normally, like as you can see in this plate on the bottom here, we have a factor of safety of 139. That's obviously really high. In the real world, we'd want to possibly reduce that because that's a lot of material that we're using. However, in this, weight reduction was not a primary concern as a lot of our materials were provided as is, and we didn't have the time or resources to machine them down to the perfect weight versus strength in terms of factor of safety. So all that compiles into what our final CAD model was, which is shown here. And this is when we could then begin building.
We were initially given a few electrical components, including an Allen Bradley 230-volt brushless servo motor and an Allen Bradley Ultra 3000 servo drive, and then some industrial push buttons as well to control them. We found out very quickly that our Ultra 3000 servo drive wasn't specifically for our brushless servo motor, and we ran into complications trying to figure out whether or not it was actually possible to power it. What we did find out is that it can power Y series motors, which includes our servo motor that we were given. However, the drive requires three-phase input as well as anywhere from 230 to 480 volts, which is well over what our advisor wanted. He wanted us to be able to plug it into the wall, which is just 120 volts AC. Since the servo drive is so old, we found out that the software for it was very difficult to find. Given it's from the 90s, it's nowhere to be found. If you went on the website and tried to get it, it required a product key, which we didn't really have because, it's old. After several phone calls and weeks of digging around, I was able to find the software on an online forum. We decided to move on to a smaller Ultra 3000 servo drive simply because it required single phase input and 120 volts AC. In doing so, wiring our system became a lot simpler and a lot more safe. This is the general electrical wiring of our system. As you can see, we have the new smaller servo drive hooked up to terminals and an external 24-volt power supply. This controls the inputs that go into the system so that we may be able to control power to the motor through the industrial push buttons. There are end stops mounted at the ends of the rails as well for additional feedback, allowing us to safely control the motor without damaging our system. Our system is controlled by a 3D printed remote connected to an 8-foot cable. This allows us to control the machine from a distance, which is much safer than if we were up close. Our remote features 5 input methods. We have a start button, which simply put, you hold the button and it drives the cart forward. Once it hits the end of the rail, or rather an end stop that we have placed, it will cut power to the start button because it runs in series, and therefore you must use the return button because that is still active, so that you can run the cart all the way back to the beginning, which also hits another end stop that cuts off the return button. So therefore you can start and stop the machine without worrying about hitting the ends. There's a fault reset button as well that allows the system faults to be reset just in case there's an error. We've had errors in the past where it throws codes and therefore the machine cannot be used. So I inserted a reset button to solve the problem. Faults generated by the system can be investigated later in the UltraWear software. We have an I/O switch that toggles the servo motor, allowing us to move the cart manually as we please. If we leave it on, the cart is held in place electronically through the servo motor. Our remote features a kill switch that shuts off the system immediately if there's an emergency. As I mentioned previously, we have mechanical end stop switches that are mounted at the beginning and the ends of the rail. There's actually 4 of them. The outer ones at the very ends do exactly what the I/O switch does, which is cut off power to the motor so that it will not continue running at the ends. We have end stops just before those that allow the system buttons to cease operation so that we may break the system, or rather so that it may stop as quickly as it can so that you can use the return button, move it back to the beginning, and go forward again. As I mentioned previously, we have UltraWear, which is the PLC software that allows us to reprogram the servo drive. With that, we can change the maximum RPM of the servo motor from 0 to 4,500 in both directions. The acceleration and deceleration rates can also be changed depending on how smoothly we want the system to drive. The maximum current that is drawn can be changed based on how much torque you need for the system. Currently it's set to 4.0 amps, but it can be increased if a larger cable is used that is rated for a higher amperage if necessary. There are also more input and outputs available for additional sensors and buttons as necessary. And this is UltraWear. This is the software that was made by Alan Bradley that allows you to manipulate the servo drive, which ultimately lets you control various components of the motor.
Here you'll see before is the completed design for the entire project. That includes all those electrical components Nova was talking about, all those mechanically designed aspects that Nate was talking about, set all together in order to send these sensors down the rail to record those fluid structures that the complex fluid lab is hoping to look at. Breaking down the cost analysis and the budget for this project, the leftmost picture here, it was our initial expected budget, and on the right is a representation of our current budget now and how those individual parts broke out. We were given a maximum amount of $2,000 to spend on this project, which included the provided rails and aluminum components, and whatever else Dr. Churi had available at his lab. Regardless of that $2,000 budget, we calculated and expected to only need 935 of that, and we stuck to that as well as we could as we went through, and found that we only required 667 with all the donations that we had, and we saw about a 30% savings from our total budget due to being able to acquire more donated parts into the project. We'll break down the BOM here, which kind of helped lead us in how we set up the project and making sure that every aspect and every item that needed to get completed was completed efficiently. We will have a list of every material that we ended up using in the project and listed who was responsible for working and acquiring that material. We also defined what was in each assembly and the level of that assembly to how far it goes from that end completed assembly of the entire rail, like we saw a few slides ago.
As you can see, our first timeline is our proposal timeline. That's the original one we thought. We thought that we would be designing and then testing and ordering parts, and then we would be finalizing and having everything done by the week of the 29th of November. But we actually ended up going all the way into December, we ended up going into the very final week of classes. Also, we didn't always meet with our advisor every single week, but we did have it blocked in. So yeah, just the very end is where we had to extend ourselves a little bit. And finally, our improvements that we are going to recommend to Churi. Dr. Churi is, first of all, is a box to hold all of the control system in. That way there aren't just wires hanging everywhere. The improved controller sheath, we would like to, have it not be wrapped in tape, but as it stands right now, it's very durable and it's very effective at what it needs to do, but just we would recommend that he makes it look a little better. Then we would put labels on the controls so they're easier for anyone who's running the machine to easily see them. Next would be calculations for upping the velocity of the cart as it moves along the rail. We would add more support to the table so it wouldn't wobble as much as it does. The wobble isn't really an issue, it's just getting rid of it. Next would be introducing an andon tower light, which is red, yellow, and green lights on it for safety. Add cable chains that would follow the cable and protect it from being cut by anything. Adding LED strips to give it better lighting of the fluid. And then lastly, we would add dampers to help preserve the rail pretty much so it didn't crash into the end of it. This concludes our presentation. So I just want to thank everyone who pitched in any time to help us. We especially want to thank Dr. George Churi and Dr. Hubner for being our advisors. We especially want to thank the warehouse where we got a bulk of our material. That saved us a boatload of money on our budget. So thank you to everyone who helped.